All right, now that we've seen some examples where we compute divergence and curl, let's talk about the physical interpretations of these quantities. So we'll start with divergence, and here's the definition of divergence up above. And notice that for a three-dimensional vector field F, the first two terms that you see in the sum, right, the x derivative of p plus the y derivative of q, that's just the 2D divergence that we had defined in the last section. Okay, so with the three-dimensional divergence, we're just tacking on this z derivative of the k component r of a vector field. Okay, and the interpretation is much the same as what we had for 2D divergence. Okay, so if the divergence is say positive at a point, then F is acting as a source near that point, meaning there's net outward flux that's being generated by your vector field. And so if I draw a little, say, ball around the point ABC, I'm going to see net outward flux across the boundary of that ball near this point. Okay, now if the divergence is negative, then I'm going to see net inward flux near that point, right? We'd say F acts as a sink near the point ABC. And if the divergence is zero at a point, then the net flux is zero near that point, right? So you can have, say, fluid flowing in to a nearby region to your point and fluid flowing out, and the contributions for the inward and the outward flux counterbalance each other, and you get a net flux of zero. Okay, we say that F is incompressible near this point ABC when the divergence is zero. And just as we had before, if a vector field has a divergence that's zero throughout an entire region in three-dimensional space, we say that vector field is source-free on that region. All right, so now let's go ahead and look at question 4 on the worksheet. And so this is actually pretty similar to some of the things we did in the last section. It says, consider the vector field F, which is x comma y squared, and here's a plot of that vector field. So part A says, does the graph suggest that well, what is this? This is the divergence, right? Just del dot F evaluated at the point -1 comma 1. So in other words, the divergence at the point P, is this positive, negative, or zero? How about the divergence at the point -1, -1? So in other words, the divergence at the point Q. Well, looking at P, right, if I were to draw a little circle near the point P, am I going to see net outward or inward flux? Well, notice the magnitude of the vectors, right, are larger up here than they are down here. So from this plot, right, we can see that there's going to be greater outward flux contributed up here than there will be inward flux from the regions down here. So for that reason, okay, the divergence at this point will be positive. How about the divergence at the point Q, right? -1, -1. Well, if I were to draw a circle here, am I going to see greater inward or outward flux? Well, I can see there is outward flux up here, but now the magnitudes of the vectors are a lot longer down here, so there's going to be greater inward flux through this little circle coming from this stuff down here generated by the field. And so for that reason, the divergence is negative at the point Q. Now part B says just compute the divergence at any point xy and confirm your answers to part A. All right, so let's do that. So the divergence, well, I'm just going to take the x derivative of the I component, p, which is 1. I'm going to add to that the y derivative of q, which is just the j component of the vector field, and that's 2y. And so if I plug in -1 for x and 1 for y, yeah, I'm going to get a positive divergence. Right? I'm going to get a divergence in this case of 3. So that agrees with what we see in the plot. And then how about at the point -1, -1? Well, here we're going to get a divergence of 1 plus 2 times -1, so that's going to be -1. And yeah, that's a negative divergence. That agrees with what we see in the plot. All right, cool. So how about part C? It says, on what region in R2 is the divergence greater than 0? Well, the divergence is 1 plus 2y. So if 1 plus 2y is greater than 0, that implies that y is greater than -1/2. So in other words, we're saying that the collection of all points in R2, x, y, such that the y coordinate is greater than -1/2 will be the region where the divergence of the vector field f is positive. And looking at this plot, y equals -1/2 is down here, okay? And it does appear that this is that transition point between net outward and net inward flux. So down here, okay, like for example, the point Q or any other point in this region below the line y equals -1/2, we can see that that net inward flux is going to be greater than the outward flux because the magnitude of the vectors of our field here is larger the, uh, the further down we go in the y direction, right? Now, up here, right, when we're above that line, then we're going to see greater outward flux. So that does make sense. Lastly, here we have D. Is the net flux across the circle C positive, negative, or 0? Explain. Well, uh, looking at the picture, the flux, remember, is measuring the normal components of our vector field as we move along this curve, right, this circle here of radius 2 centered at the origin. And then this thing is, the integral is summing those normal components. Okay, so are we going to see if I imagine this is describing, say, the velocity of some fluid flowing throughout the xy plane, are we going to be seeing greater outward flow or inward flow? Well, we definitely see some inward flow down here across the boundary. But then when we're above this line y equals -1/2, then this is all going to contribute positive uh, flux, right? So in other words, outward flow up here. And that's definitely going to outweigh the inward flow down here. So this should be positive. Now, you can go ahead and check the actual outward flux is 4 pi. Not that you actually have to compute it. It's clear from the picture, but nonetheless, it does turn out to be a positive 4 pi there, but that is definitely consistent with what we're seeing in this picture. All right, well, that's going to do it for this problem. I'll see you in the next video.